Welcome back to Talking Science Interviews. Matt Miller with you in Studio 4. Today, it's all about things on a massive scale, magnetars in particular. Marcus Lower is my guest. He's a PhD student at the Swinburne University of Technology. They've been studying this magnetar, J1818 they like to call it. It's revealed some very interesting things. It's one of only 30 that have been discovered in the universe, and Marcus is going to chat to us about what this discovery entails on this Talkin' Science Interviews.
On Apple Podcast, Spotify, Google Podcasts and YouTube for over 550 episodes. This is Talkin' Science.
Marcus, thanks for a little bit of your time on today's Talkin' Science Interviews. Really appreciate it. There's a big thing happening in the universe called magnetars. What are they?
So magnetars, they're a kind of neutron star. So these are the collapsed remnants of massive stars that reached the end of their lives, underwent a supernova, and then collapsed into, well, their cores collapsed into a very dense object. It's about 20 or so kilometers across, but weighs anywhere between 1 to 2 times the mass of the sun. So they're very dense objects. But magnetars are a very special kind of neutron star. So whereas like an ordinary neutron star has a magnetic field that's maybe a few billion times the strength of the Earth's, magnetars have magnetic fields that are 1,000 times stronger than ordinary neutron stars.
Wow.
Yeah, so you can, they're pretty complicated. Oh yeah, they're quite complex and they're quite energetic objects because they have a lot of stored energy inside them.
Not something that you want to get close to or necessarily be orbiting around if you manage to survive that close.
Yeah, absolutely not. I mean, even just an ordinary neutron star, you wouldn't want to be anywhere near it. A magnetar, that's kind of sort of danger is kind of magnified by many orders of magnitude.
And it's also that magnetic field as well. There's an analogy that if one of these magnetars was as close to the Earth as the moon, we wouldn't be able to have magnetic key cards at all. That's just how strong it is. If hypothetically we were to survive being that close. But these magnetic fields are obviously so strong and just what they do. So, Marcus, let's talk about the magnetar that you've been studying, Swift J1818.0-1607. Now, I know how much astronomers love a good acronym. Have you got one for this magnetar?
We've just referred to this one as J1818 to keep it short.
Swifty, maybe?
There's actually a few magnetars called Swift. So, yeah, it's one of these things that how the magnetars are named is typically the Swift is the name of the satellite that discovers it. And then the sort of phone number, if you will, is just its position on the sky.
Well, that is very interesting. And it was first discovered in March 2020. It emitted a bright X-ray burst. Was it sort of a happenstance? Were you looking in the right direction for this one, or were you looking for it to begin with?
So this was actually what is referred to as a blind detection. So the Swift satellite, the space telescope that was that discovered the magnetar, it performs these all-sky searches all the time, looking for all sorts of high-energy events like gamma-ray bursts or X-ray bursts. And it just happened to be looking in the right part of the sky when this particular magnetar gave off this burst. And then it very quickly swiveled over to observe it with a sort of a narrower field of view telescope to kind of pinpoint exactly where it came from. So this one we weren't looking for. Other ones that we know about previously, we have looked at with radio telescopes, but we haven't seen them.
And what's special about this this magnetar 1818?
So there's actually quite a few things that are special about it. So for one, it's the fastest rotating magnetar that we know of. So it spins once every about 1.5 seconds, which is it's pretty slow for neutron stars, but for magnetars, that's pretty damn quick. It's also possibly one of the youngest neutron stars that we know of. So based on both how quickly it's spinning and how quickly that spin slows down over time, you can get an estimate of how old that magnetar should be, and it's only about 1,000 years. That works out to be only about 1,000 years. So it's incredibly young. And I guess the final thing about it that's kind of really interesting is that it's only the fifth magnetar that we've actually discovered that not only does it emit X-ray pulses and gamma rays, but it also emits radio pulses. Now, these are very rare magnetars. There's only 6 that have been discovered so far out of the 30 or so magnetars that we know of.
And it's also flipping between the magnetic poles as well, which makes it very interesting as well.
Yeah, so that was this interesting discovery we made with the Parkes telescope. We were watching it evolve over 6 months after it was discovered, where we noticed that the radio emission from it seemed to flip between 2 different magnetic poles. Now, what's kind of curious there is that the magnetic poles don't seem to be on opposite sides of the neutron star. They appear to be kind of co-located. So you have one that's just a little bit below the equator in the southern hemisphere, and one that's just a bit above the equator in the northern hemisphere. And you're right, it did actually, between some of our observations, appear to flip between these 2 poles, which, to my knowledge, hasn't actually been seen before in a magnetar, let alone any other radio pulsar.
And could the flipping of the poles have something to do with the radio emissions?
So in this case, so it's not the poles itself that's flipping, it's the plasma where the radio emission comes from.
Oh, okay.
So in neutron stars' magnetic field, it has all these particles that are flowing off of the surface just because of the really strong magnetic field. And in doing so, those particles then radiate electromagnetic waves, some of which appears as radio waves. In this case, it seems like the emission region, so where the radio waves are coming from, were primarily found around this magnetic pole in the southern hemisphere. But occasionally they seem to flip to this northern hemisphere magnetic pole. We don't know exactly why it does that. We know that this magnetar has a very dynamic and ever-changing magnetic field. That's something that we actually, we want to try and explore further in the future.
And I guess one theory is that it could have evolved from a more regular pulsar over time. So finding new stuff about these magnetars, as you say, there's only been 30 of them discovered. So a really young field of astronomy to be looking at, and plenty of discoveries to be made in the years ahead.
Absolutely, yeah.
Fantastic, Marcus. Well, I really appreciate a little bit of your time talking about magnetars today. This discovery is absolutely fantastic. Good luck continuing to observe 1818, and hopefully you can unlock some more of its secrets.
Yeah, fingers crossed we get time on the telescope. But yes, it's been a pleasure talking to you. Thank you very much.